Yeah, last lecture we talked about equivalence classes and equivalence relation. Now we're going to talk about a very important equivalence relation and a very important what the equivalence class looks like for a group. And again, this is what's going to help us to make that answer the question. Initially, remember when I introduced equivalence relation, I said, we've seen in some examples that when the group is finite, the order of any subgroup will divide the order of the group. Does this hold in general? And let's see, the machinery to do this is equivalence relation, and particularly process. So we have GA group. For all A, B, and G, we define a relation A congruent to B if A B inverse what is an element of H. So I should say, erase this here, G a group, that's still true. G a group, H a subgroup of G. We write for this A will do triple I equal B mod a subgroup. So let's show this is an equivalence relation. Again, I may have some more details in the notes. But just the rough idea we have, first of all, is A equivalent to A mod H? Well, A times A inverse is equal to E, and any subgroup is a group, so it has the identity, which is in H, not equal to, in H. So A is congruent to itself mod H. So this congruent mod H is reflexive. How about symmetric? Suppose A is congruent to B mod H. So A B inverse is in H. But H is a subgroup, so H's group is closed under inverses. So the inverse of this is in it. But I think that's going to be just B A inverse is in H. And that's sort of a general property of how you take the inverse. Here we'll just actually verify. Note that A B inverse times B A inverse, these two soak up, become E. Equals that. And that would equal E. So I think that tells me that the inverse of A B inverse is just BA inverse, right? Because if I multiply this on the right by BA inverse, I get back the identity. So what does that tell us? So that tells us that B is congruent to A mod H. So we've now shown symmetry. So we've shown reflexivity, we've shown symmetry. How about transitivity? So assume that X is congruent to Y mod H, and also Y is congruent to Z mod H. So what does that tell us? So that tells us that, so XY inverse is an element of H, and YZ inverse is an element of H. But H is a subgroup, so not only is it closed under inverses, it's closed under multiplication. So the group operation applied to these elements must still be an H. But you can see this is just going to end up being XE, Z inverse is an H, XZ inverse is an H, and by golly, that's exactly what it means for X to be congruent to Z mod H. So we have an equivalence relation. Let's just remark on a previous relation. Let's revisit congruence mod M. So let G be the integers, and let H be the cyclic subgroup, and given a positive integer n, let H be the cyclic subgroup generated by n, which is basically, as we've seen when we looked at the group structure of the infinite cyclic group of the integers, all multiples of n. Now put in quotes, what does x, y inverse in this group mean? Again, we think multiplication in the abstract, but gee, the integers are a group, what's the operation? It's not multiplication, right? There are no inverses. The integers is a group under addition. So you should think about this as really x combined with the inverse of y. Well, combined means add, because that's a group operation. And the inverse of y is negative y. So it would be x plus a negative y is in M. Or x minus y is an element of M. If M is, but M are all multiples, that means x minus y is a multiple of M. So M divides x minus y. So really this equivalence relation we defined just from division of the integers mod M, that's really a special case of this general relationship in a group of congruence mod a subgroup, where for the integers mod n, we pick the subgroup is the cyclic group generated by that positive integer n. And again, in the abstract, we don't know what the heck the group is, we just write x times y inverse. We use the multiplicative notation. But now we actually have a concrete example where we know the group operation is in fact addition. So that's why you quote unquote x y inverse is really x and the inverse of y combined under the group operation. The group operation being addition. So let's look at the equivalence classes. What are the equivalence classes determined by? Again, where G is a group and H is a subgroup of G. Okay, so let's see, what do they look like? So what is the equivalence class? Let some element in G here. So the element of G is all those x's in G that are equivalent to A. So what does it mean to be equivalent? It's all those x's such that, so x is equivalent to A would mean x A inverse is an element of H. And so what I claimed is, you can almost think, if you think about, if you just multiply by A on both sides, you have x is an element of H times A. So what I claim, the equivalence class determined by A is exactly hop H times A, which is a set what you do is you let H run through all the elements in the subgroup H, and you multiply on the right by A. So how do we show containment of sets? We try to show double inclusion. Everything on the right set is on the left-hand side. Everything on the left-hand side is in the right. So let's try to show that. So let's take any element in A and try to show that X is in that set H times A. So let X be in A. So if it's equivalent to A, that means, we've seen that means X, A inverse is in H. So there exists a little h in H with X, A inverse has to equal little h. So if I multiply on the right by A on both sides, or X is equal to HA hop. And H is an element of this subgroup H, so that's in this. So I've taken any X in the equivalence class determined by A, and I've seen that X is in this set HA. So that shows that this subset is contained here. What about the other containment? So to show that this set HA is in this equivalence class, take any element in HA. Basically, you just work that backwards. There exists an element in the set H with x equals little h times A. So if we multiply on the right by A inverse, x A inverse equals H A inverse, or x minus A is equal to H, which is an element of the set H. In other words, just writing it again, x A inverse is an H. That means that x is congruent to A mod H, and so x is equivalent to A, x would have to be in its equivalence class, and that's what we wanted. So we've shown that the HA is contained in the equivalence class A. Which completes the proof of my claim. And the set HA is called the right coset determined by A. I usually say re H. You have to cite the subgroup. Okay, it's called, actually it's maybe called the right coset of H determined by. My math teacher said, well, why is it right or left? Why is the, because you could say, well, the A is on the right, but the H is on the left. But she explained to me, she said, well, in math we value the individual. So the way she remembered it is, we want to value the individual. So when the individual element is on the right, and the big set of all these elements are on the left, we single out the individual element, the right coset determined by A. So what's so special about the right? And there really is nothing. We can determine left cosets. So one can also show that given a group G and a subgroup H, if we define for any two elements in the group G, A congruent B mod H. And to distinguish it from the right coset, even though maybe it's right-handed bias, when we talk about the right cosets, and we just will put the 3 equal sign, when we're talking about the left, I'll put a little L here. Fine, so you might remember we defined A is equivalent to B if A times B inverse is an H. Now we reverse it the other way if B inverse times A is an H. So this will be an equivalence relation. I don't have this in the notes currently, so I can try to show it here. Look at for all elements A and G, A inverse times A is equal to E is an H. Be very similar arguments. So A is left equivalent to A mod H. Give me a second to just erase that. Oh, before I erase it. So they really are very similar arguments. I'll just to get some practice with some proof writing, I'll go through and show them. For any 2 elements in G, if A is left congruent to B mod H, then B inverse A is an H. And we want to note that B inverse A times A inverse B is just going to be the identity, which is an element of H. Or not, well, maybe an element of H, we don't care about that. So that means the inverse of B inverse A is equal to A inverse B. And since H is a subgroup, and B inverse A is an element of H, the inverse of this is an H, but we've just seen that means that A inverse B is an element of H, and that is B is left congruent to A mod H. So we proved reflexivity, symmetry. How about transitivity? Again, just like before, we take 3 elements, and not H and G. And we assume that A is left congruent to B mod the subgroup H, and B is left congruent to A mod the subgroup H. And so, what does that mean? That means that B inverse A is an element of H, And, oh, what's wrong here? A is equivalent to B, B would be equivalent to C. And C inverse B is an element of H. So since H is a subgroup, the product must be in there, so B inverse A times, and again here the product doesn't matter, any two elements, so let's multiply this element on the left and this element on the right is in H. But you see these will just cancel out. We're going to have the identity. So C inverse A is in H, which means that A is equivalent to C mod H, or left equivalent. And so we have the transitivity property. So we do have an equivalence relation. So we'll close this lecture by looking at the looking at the equivalence classes. And you might think, well, we saw in the regular mod H, when we look on the right side, the equivalence classes were the subgroup H times an element A. That was equivalence class determined by A. So we wonder, maybe A on the left will be the equivalence classes determined in this relation. So let's look at that. So left H, and maybe I'll put a little L here to indicate I'm talking about the left, all the elements of the group such that X is equivalent to A mod H. In other words, everything in the group such that A inverse X is an element of H. And again, I claim that this equivalence class is just A times H. So let X be an I. So there's an element in H with X equals AH. So if I multiply on the left by X inverse, by A inverse, but this is the identity, so it's just going to be an H. So A inverse times X is an H. So that means that X is equal to A under this equivalence relation mod H. By definition, that's exactly what it means to be in an equivalence class. Okay, what about the other way? So what have we proved here? We've proven that AH is a subset of that equivalence class. What about the other way? Maybe instead of x, let's just use a different variable like z being this equivalence class. So again, that would mean that A inverse z is an element of the subgroup H. So just like before, A inverse z is equal to H. And so if I multiply by A on the left to each side, we get z is equal to AH. So the left equivalence class determined by A is inside of AH. And so together, both of these prove the claim. And then, again, we value the individuals, so this set AH is called the left, because the individual element is on the left, coset of H determined by A. So we'll stop this video here. We'll be talking some more about cosets, but we'll just take a break at this point.